first thing first, the one thing that makes alkynes distinctive compared to alkenes is the acidity of terminal alkynes. As you guys know, terminal alkynes are highly acidic because the conjugate base, the carbon is sp, and the hybridization stage of the carbon makes the conjugate base highly stable. So that means that we can treat an alkyne with a strong base as, for example, sodium amide, and that allows us to form an acetylide ion, which is a very strong Lewis base that we can subsequently use in nucleophilic substitution and elimination reactions. So if we, as I said before, and I'm gonna repeat this again, guys, when you use acetylides, we just went over that a few minutes ago. You must use a primary heteroalkene. If you use a secondary heteroalkene, the major product is elimination. So you only use acetylides for nucleophilic substitution in an SN2-like reaction by using primary halogens, okay? Never, ever secondary. So this is a classic SN2 reaction, so pretty simple. And that leads to, and this is something is quite handy for synthesis later on. So you can use alkynes for synthesis purposes, since it allows you, this acidity of the alkynes allows you to make a carbon-carbon bond forming reaction. This is an sp3 carbon bond reaction. Okay. So that can only be done with alkynes. Obviously, you cannot do it with alkenes, which are not acidic at all. So that's the number one thing about alkynes that is different. The second, so we also learned in class how to make alkynes. Remember, we can practice a little bit of retrosynthesis now. We can make an alkyne by means of two E2 reactions, and the organic substrate for that is a dibromoalkane. So we need to have a 1,2 dibromoalkane, and two subsequent elimination reactions will lead to an alkyne. Details that we need to keep in mind here is a terminal alkyne. For terminal alkynes, we need 3 equivalents of the base, because the terminal alkyne, as I just mentioned now, they are quite acidic, so they will react with the base. So we need an extra equivalent to account for this reactivity. And then if you want to get the alkyne, not the acetylide ion, then obviously you need an extra step of hydrolysis. Okay, so that's how we make an alkynes, two subsequent substitution elimination reactions of a 1,2 dibromoalkane, classic E2, leaving group and bromine must be anti-coplanar. We just discussed that. Okay, how do we make a dibromoalkane? Just learned that, discussed that a few minutes ago. We just need to do a bromination of an alkene. Bromination of an alkene. Bromonium bridge is the intermediate. We know that we just discussed the reaction. Stereospecific, anti-stereoselective, all these things. How can we make an alkene? A single E2 reaction using a strong base, like for example, sodium amide could be an example of that. Is an example of this, and the organic substrate that we need for that is a bromoalkane. Okay, and how do we make a bromoalkane? Radical substitution reaction, right? Oh, radical substitution, so just bromine and light. This is a little bit of synthesis practicing. Br2 and light. Radical substitution. When you do these synthesis problems, guys, practice the mechanism. Think about the slowest step, the regiochemistry, stereochemistry, everything, right? So bromination is regioselective. That's why you get substitution only at the secondary carbon here. Elimination, anticoplanar, bromonium bridge, electrophilic addition here. Two elimination step, you get to the alkyne. Okay, so that's how we make an alkyne. Step two. Step two is going to be now, so what kind of reactions have we learned with alkynes? So alkynes can be used in all kinds of electrophilic addition reactions. We discussed that in class 2.
Professor, I quickly have a question on the SN2 mechanism with alkynes.
Can you repeat again, please? I had to step out for a second.
No, sorry. Yeah, I just have a quick question with the SN2 mechanism with alkynes. So you know how we have the installation of the alkyl groups? Say we have like you want to install a methyl and then an ethyl. Those two steps are done separately, right?
Yeah, otherwise you will get a mix.
Okay, thank you.
So reactions that we discussed with alkynes, electrophilic addition reactions. Addition of hydrobromic acid. So remember, I discussed also in class. Anybody remember who is more reactive to electrophilic additions reactions, alkenes or alkynes? I asked this in class a couple of times.
Is it alkanes because of S character?
Is the alkenes because remember, so if we talk about reactivity, we need to think about electrophilic addition reactions. The slowest step in electrophilic addition reaction is formation of a carbocation, right? So that's the slowest step in electrophilic addition reaction. The carbocation formed by an alkyne, the carbon is sp hybridized. And the carbocation formed from an alkene, that's sp2 hybridized, right? So carbocations are electron deficient. So we want certainly we don't want an electron deficient carbon to be electronegative. So because of this, the carbocation coming from alkenes are way more stable than the carbocation from alkynes. So that means that makes alkenes way more reactive in electrophilic addition reactions as compared to alkynes. Okay? So keep that in mind. So electrophilic additions of alkynes that we learn in class, for example, hydrogen halides, again, formation of a carbocation that we discussed this in class. In the text, we will find the mechanism. If you use an excess, the reaction is regioselective, and you will end up with the both bromines in the same carbon. You can do the mechanism later, or it's in the text once again. You'll see why in both cases the carbocation is more stable with in the second carbon. So so we discussed that in class. We talk a little bit about the one important reaction here was the hydroboration oxidation. So in that case, we were talking about the formation. Once again, remember hydroboration oxidation is forming for alkenes and alcohol regioselectively. So here, when we get a terminal alkyne, we need to use a bulky borane, remember. So that's the thiamyl borane because we want to avoid the side reaction of the terminal alkyne. So keep that in mind. So we need to use a bulky borane. So that leads to an enol. The only difference compared to alkenes is that now we have an extra pi bond. So instead of an alcohol, we get an enol. And enols are in tautomeric equilibrium with keto forms. So in this case, we will end up with an aldehyde instead of an alcohol. So the reaction is regioselective because once again, the enol is formed in the lowest substituted carbon, since that's the carbon where the bonding will be bonded to. Okay. So we also discussed the acid catalyzed hydration of alkynes. I just talk about how alkynes are less reactive than alkenes. So for acid catalyzed hydration, we need to use stronger electrophiles as compared to alkenes. So we use mercury sulfate in sulfuric acid and water. So acid catalyzed hydration follows the same pattern as oximer creation. So we got a mercurinium bridge in step number 1, and then water, who is the nucleophile in step 2, will be attacking. So I'm gonna try to draw the mercurinium bridge for you guys here. So we got a mercurinium bridge here. In this case, we have H2 plus. And then the nucleophile, in this case, once again, water, for the same reasons as in oximer creation, is attacking only the highest substituted carbon of the mercurinium bridge, is the carbon that is more electrophilic, the carbon with the highest partial positive charge. So it's opposite regioselectivity as compared to that of hydroboration. And that leads to an tautomeric equilibrium, then protonation. So you got the mechanism in the textbook we did in class 2, and I'm gonna draw the whole thing here because it will take some time. Bottom line is the enol is formed in the highest substituted carbon of the triple bond, and that leads to a ketone instead of an aldehyde. Okay, so you can form aldehydes or ketones from terminal alkynes by means of hydroborations or acid catalyzed hydration reduction. We also discuss here reduction reactions. You can obviously reduce an alkyne all the way to an alkane. More importantly, we can, well, it's not going to apply in this case, so I'm going to give you another example. We can also reduce it to halfway through to an alkene with specific stereochemistry. So in that case, we can say, let's say we use the Lindlar catalyst and then hydrogen, so classic hydrogenation, but using the Lindlar catalyst. Don't forget to put hydrogen, guys. It's important because if we don't have hydrogen, there is no reduction. So keep this in mind. Lindlar catalyst stop the reactions, the reduction right in the alkene, and it allows you to do it with specific stereochemistry. In this case, produces the cis alkene, very important for synthesis purposes. We also study in class a way to get trans alkenes, and that would be, it's actually a radical mechanism. You don't need to know it for the final exam, but it's in the textbook. It's pretty nice if you want to take a look at it. So it's the reduction with the lithium or sodium methyl and the presence of ammonia. That's where the hydrogens are coming from NH3. And that allows you to get the trans alkene instead of the cis one. So you can reduce, once again, an alkyne all the way to an alkene, but you can also reduce it to alkenes with specific cis or trans stereochemistry, depending on the reaction mechanism. So this is a radical mechanism. This is a catalytic hydrogenation mechanism.
We don't need to know the radical mechanism for lithium
No.
and NH3? Oh, okay.
No. No need to worry about that. So what I want you guys to know from alkynes is this basic reactions, and then obviously how to make an alkyne and how to use it to make carbon-carbon bonds. Okay. You can also use alkynes to open epoxide rings. I just gave you an example.